Hi, we are from group BigPotato and I'm Poh Lok Yee. So now we will be presenting our project 1, which is having a title of Optimizing High Performance Data Processing for Large-Scale Web Crawlers. The Malaysian job market contains a large number of job opportunities on the job street. However, the manually collecting the job information from thousands of listings is very time-consuming, inefficient, and also impractical for large scale of analysis. So to solve this problem, we have developed a high-performance computing-based web scraper that automatically collect and process the job data from the job street. So by applying the parallel processing techniques, so our system can efficiently extract more than 100,000 job records for the further analysis. So on the right side is our objectives of our project that we want to achieve. So we aim to collect over 100,000 of job records, build an automated data cleaning and pre-processing pipelines, optimize the crawler using the multi-threading, multi-processing, and asynchronous programming, and finally compare the execution performance before and after the optimization to evaluate the effectiveness of these techniques. For the first phase of our project will be the data collection part, which is the most important part, that how we get our data from the data source. So from here, we can see that this is our overall data collection process for this project. So first, our data source is the job street Malaysia, where we target more than 100,000 of job records. So for each job listing, we collect information such as the job title, company, location, salary, and also the classification. So the crawling process is handled by three main components. So first is the essential, which it runs the 8 concurrent workers to crawl multiple pages simultaneously to improve the scrapping speed. So next, the playwright will load the dynamic job street web page and renders the content. So after the page is fully loaded, the beautiful soup will process the HTML and extract the local job information. So this process is repeated through a pagination loop across every page and also the job classification until no more records are available. So finally, all extracted data is stored as a JSON file, which producing a total of 105,094 job records. So from here, this is one of the example of the raw data that we get from the JobStreet website. And here we get the job title, the location, the classification, company, and also the salary as 5 attributes that we want to get. And all of it is stored inside a semi-structured JSON file. And it will be passed to the data processing stage at the next.
Next, I will be explaining on the data processing stage. So in this stage, the raw job street dataset has to be cleaned, transformed, and also converted into a structured dataset that was ready for further analysis and also performance testing. The raw dataset initially contained about 105,000 of rows and 5 columns. So during the data cleaning, duplicate records were removed, which reduced the dataset into remaining about 26,000 rows. So after that, rows with missing required fields like the company name or job title, all these rows were dropped. While if missing salary values only, it was filled with the words not disclosed. So instead of removing them, so after missing value handling, only left 26,074 rows remain. So next, the data was transformed by cleaning extra white space, standardizing job classification, location, and also removing job titles that contain non-ASCII characters like all the Chinese words. And the salary text was also separated into two numerical columns, which were the salary minimum salary, and also maximum salary. So after all these pre-processing steps are finished, the final clean data set contained only about 25,000 rows and also 7 columns. So now this slide actually shows the structure of the final clean data set. So it contains 7 attributes, 7 rows, 7 columns, which are the job title, company, location, classification, the original salary text, the minimum salary, and also maximum salary. So the original salary column was retained for reference, while the salary minimum and maximum salary is added to support the numerical calculations after that for the analysis. So the final data set was saved in the CSV format and was ready for optimization step.
Okay, so for my part, I'll explain the optimization techniques used in our job street data processing pipeline. So after the data was cleaned, we applied 3 different optimization approach, which are pandas, polars, and duckdb. So for pandas, the main focus is on the memory optimizations, vectorized operations, and efficient grouping. This will help to reduce the unnecessary memory usage during the data loading and processing. And for the polars, the main optimization is lazy evaluations, query optimizations, and parallel processing. This means Polar does not immediately execute every step, but instead it will optimize the query first and only runs it when needed. And lastly, for DuckDB, we use the SQL-based analytical processing. It can directly query the CSV files and perform optimized aggregation without fully loading the entire dataset into memory. And overall, these three approaches will help us to process the clean job street dataset more efficiently and prepare it for the performance comparisons. Okay, so now I'll explain the three frameworks in more detail. So for the pandas optimized pipeline, we loaded only the required columns using use columns and specified the data types using data type and converted the repeated values into category. And also we also use the vectorized strings operations and group by to make the processing more efficient. And next, for the Polar's lazy executions, we use scan CSV for lazy loading. This means the operations are not executed immediately, but only when .collect is called. Then the operation is executed. Polars also supports the parallel aggregations, which helps to improve processing speeds. And lastly, for DuckDB SQL processing, we use the read CSV auto to query the CSV file directly. It supports the SQL filtering and aggregation using group by, count, and count distincts without fully loading the whole dataset into memory. So overall, the pandas focus on memory optimizations, the polars focus on lazy and parallel processings, while the DuckDB focus on SQL-based analytical processing.
Okay, hi, I'm Cheryl. So now I'm presenting the performance evaluation. Okay, moving to the visualization slide. So here we present the resource telemetry metrics across the 4 key performance indicators during the data processing phase. So first, we can see that the execution time on the top left and the throughput on the bottom right. It visually evidences that the Polar's lazy execution dominate the field. So it achieved the shortest processing duration and the highest throughput, shows that it exceptional parallel computing efficiency. So next, regarding the memory usage on the top right, so the baseline implementation generate a massive resource overhead. On the other hand, our optimized pandas remain the remarkably low, almost flat to the bottom. So this strongly validate the effectiveness of our optimized technique, specifically dynamic type specification and the selective column loading. Finally, we observe the CPU usage on the bottom left. So the Polar managed to deliver the faster performance while maintaining the lower CPU utilization, which further proved the highest resource efficiency of its underlying Rust engine. Okay, now, so let's move to the next slide. So this table summarizes the performance comparison of the different data processing approach. So first is absolute processing speed and high concurrency are parity. So Polar clearly stand out as the best performer. It achieved an average execution time of just 0.07 seconds, delivering an impressive throughput of over 400,000 rows per second. So while utilizing only 16.88 CPU resource. So this demonstrates its exceptional efficiency in handling data-intensive workloads. So second, when operating in memory constrained environment, the optimized Panda provide the most lightweight solution. After applying our optimization technique, its average peak memory usage was reduced to only 0.001 MB, compared to the 3.92 MB in the baseline version. So this significant reducing highlight how effective code optimization can greatly improve the memory efficiency. Okay, lastly, for the DuckDB SQL, our job script dataset is only medium size, so its performance was slightly affected by the engine's initialization overheat, resulting in an average execution time of 0.23 seconds. Although it did not outperform Polar in this experiment, so the result provide a valuable benchmark for future system expansion, especially when scaling to million row dataset, while DuckDB string are expected to become more evident.
So to summarize, in conclusion, this project successfully developed a complete job street data pipeline covering all the data collection, cleaning, transformation, optimization, and also the performance evaluation. So a total of about 105,000 of raw records were processed into a clean data set that containing about 25,000 of rows and 7 columns. So 4 processing approaches were compared, which is the baseline pandas, the optimized pandas, the Polars lazy execution, and also the DuckDB SQL. So among them, Polars achieved the best overall performance, showing that the optimization techniques can improve processing speed and also efficiency. So next, for the future work, the pipeline could be tested using actually more than 1 million records is better to evaluate scalability more clearly. So after that, a more reliable cloud server could also be used to obtain more consistent benchmark results. And the system could be further improved by adding complex joins and transformation also, and replacing the CSV format with Parquet is better to store data in PostgreSQL or MongoDB. And we also can automate the workflows using Apache Airflow, and implementing an incremental crawling to collect all the new updated job listing. So that's all from our group. Thank you.